Welcome, my dear students. So, in the previous lectures, we have discussed about linear functionals and some of its examples. Without discussing further into linear functionals, we need certain set of definitions to proceed. So, in this lecture, we will be discussing about some definitions which will be essential for our study. The first definition is algebraic dual space. So, in a given vector space X, you can define a function onto some K, which is the underneath scalar field, and if this function is linear, then that function is called linear functional. So on a vector space, you can actually define a lot of linear functional as well. The classic example is we have defined on CAB for all T naught belongs to closed interval AB. We have defined fx as x of T naught. So corresponding to each T naught belongs to closed interval AB, we can define a linear functional in CAB, the vector space. So there are lot of linear functionals which is defined on a particular vector space, and if we collect the all collection of all linear functionals defined on a vector space, that space is called the algebraic dual. So X is actually a given vector space, then the collection of all linear functionals defined on X is called the algebraic dual space. It is usually denoted by X star, and it is also a vector space. It is a vector space using the following operation. The sum is defined as for any f1 f2 belongs to x star, and for every x element of x, f1 plus f2 should be equal to f1 plus f2 of x, which should be equal to f1x plus f2x. Okay, so this is actually the sum which is defined on x star. Similarly, we can define the scalar product as well. So the scalar product is alpha f1 is equal to alpha f1 of x, which should be equal to alpha times f1 of x. So this is actually the sum, and this is actually the scalar product. Using these two operations, x star forms a vector space. So the collection of all linear functionals which is defined on a particular vector space forms another vector space which is called the algebraic dual of a particular vector space. Now, since x star is also a vector space, so instead of x we can replace x is equal to x star on the definition. That is, we are collecting set of all linear functionals defined on algebraic dual. Okay, clearly this is also a vector space, and this is called second algebraic dual, and it is usually denoted by x double star. Okay, so x double star consists of the collection of all linear functionals which is defined on x star. Please understand that every element of x star is a linear functional. Okay, so if we collect the collection of all linear functionals on x star, which again forms a vector space, which is called the second algebraic dual x double star. And the important aspect is that this x double star has a complete relation with regards to the original vector space x, or x and x double stars can be related using certain functions. That's why we study x and x double star in general. So every associated with every element of x, we can actually define an element in x double star. So there's a specific type of relation which relates every element on a vector space to every element on its second algebraic dual. That's why we study this. We study about these duals and second algebraic duals in details in the next sections. Let's move on with our definitions. As I have already told you, you can actually obtain a specific relation connecting x and x double star. Okay, so for every x element of this x, the vector space, you can obtain a g which is defined on x star, a linear functional which is defined on x star which belongs to x double star. So such a definition is obtained as such as this. So corresponding to every g belongs to x double star, which is a linear functional, on x star, which means the x star contains set of all linear functionals on x. So every element of x star should be of the form some f, where f denotes a linear functional from x onto some scalar field. And choose a fixed x, element of x, and set gf. So I choose gf because g is defined on x star consisting of all linear functions which is defined on capital X. Usually it is denoted by small f. So gf should be equal to gxf, which is what we are going to define, which should be equal to f of x. So the definition is, corresponding to each x in capital X, we can actually define a linear functional on x star, or a g which belongs to x double star, which connects them together by a relation g of f is equal to f of x, where x is fixed and g is f is varying. Okay, so this is the relation connecting x and x double star. And also this gx, which defines a linear functional on x star associated with a fixed x belongs to x, is actually a linear. So gx is linear. So that is gx of alpha 1 f1 plus alpha 2 f2, because gx is defined on x star. X star consists of linear functionals. f1 f2 are linear functions and alpha 1 alpha 2 are scalars. By definition, this should be equal to gx of f should be equal to f of x. So gx of this should be equal to alpha 1 f1 plus alpha 2 f2 of x, which by definition of sum should be equal to alpha 1 times f1x plus alpha 2 times f2x. So it should be equal to f1 of x should be gx of f1, f2 of x should be gx of f2. So alpha 1 times gx of f1 plus alpha 2 times gx of f2. So this clearly indicates that gx is actually a linear operator. So to sum up the whole thing, for each x element of capital X, there exists a linear operator gx belongs to x double star, and which means that associated with every x we can actually find an element in x double star. Associated with every element in capital X, the vector space, you can always find an element in the second algebraic dual. So we can actually define a function c from x to x double star, which maps every element x onto its corresponding gx. This map C is called canonical mapping. This C is called canonical mapping. Also, C is linear as well. So C is linear. It's understood that C has a domain capital X, which consisting of the element small x. Okay, so C should be linear with respect to this. So take C of some alpha x plus beta y of f, because in order to go past, in order to connect an element x to an element in x double star, we must go through x star. So x to some f of x which connects to g of x. So this is in x, this is in x star, this is in x double star. So c of alpha x plus beta y, here assume that this is actually the variable where x and y are actually element of the space x, which should be equal to, by definition, x maps onto gx. So this maps onto g of alpha x plus beta y of f, which by definition should be equal to f of alpha x plus beta y. Since f is a linear functional on x, this should be equal to alpha f of x plus beta f of y. So f of x can be written as gx and f of y can be written as gy. So this can be written as alpha gx plus beta gy. And also we have defined that C is a map which connects x onto gx. So C of x should be equal to gx, and c of y should be equal to gy. So which we can write as alpha cx of f plus beta cy of f. We use this f because in order to connect an element x with respect to an element in x double star, we must go through an f in x star. That's why we define this. So clearly c of alpha x plus beta y should be equal to alpha cx plus beta cy. So which means that c is actually linear. So the canonical mapping which connects every element x onto some element in the second algebraic dual is always linear. Now C can also be sometimes called, C is also called canonical embedding as well. Now this term embedding should need to be explained a bit more detail. Okay, that's what we are going to do. So there are spaces, two spaces x and y. We denote x and y. They usually don't look alike. They are two different structures, but they may be connected by some functions which may make them look alike. Such functions are called isomorphism. Or there are there are actually structures, two different structures whose elements may not be the same, whose element may not look like the same, but the properties of the two structures should be completely same. Such structures in our study are essentially same structures because we do not need a structure which has the same property with another structure to study in detail because two structures are essentially same. So even though their elements may not be same, the structural properties are always should be same. So these two structures are connected by a function which is called the isomorphism. So we have also already defined the an isomorphism in the case of metric spaces. So let two metric spaces xd and yd bar be two metric spaces. An isomorphism T from x to y is a bijective mapping. It's a bijective mapping which preserves distance. That is d tilde of tx ty for some element x in y x should be equal to d of x comma y. So if you take two arbitrary elements x and y in capital X and maps its element onto tx comma ty in y, here d is the metric, here d tilde is the metric, then with respect to d tilde the distance between tx and ty should be same as the distance between x and y. So a bijective function which preserves the structure, the underneath structure. Here the underneath structure is related with the metric. So a bijective function which preserves the underneath structure is called an isomorphism, which means that even though the metric may not be look alike, even though the two spaces elements may not be look alike, these two spaces are essentially same. So these two spaces are isomorphic. Similarly, in the case of two vector spaces, we can define an isomorphism as well. So x comma x tilde be two vector spaces spaces over the same field. So a bijective mapping which preserves the two algebraic operation of the vector space is called an isomorphism. That is, if t from x to x tilde is said to be an isomorphism if for every x comma y, if for all x comma y belongs to x and some alpha belongs to the scalar field k, t of x plus y should be equal to t of x plus t of y, and t of alpha x should be equal to alpha tx. If such a bijective map exists between x and x tilde, then that bijective map is called an isomorphism, which means that in terms of a vector space, even though the elements of x and x tilde are different, structurally they are actually same. So any bijective map which preserves the structural composition is called an isomorphism. If in connecting two different spaces there exists an isomorphism, which means that structurally they are actually same. They do not have different properties in terms of the structure as a general. Or if two vector spaces are connected by a bijective linear operator, then the two spaces are actually isomorphic. That's the basic idea. And we have already defined, we have started this discussion by defining canonical embedding. And C is actually a map from x to x double star, where x and x double star are actually vector spaces and C is linear. Okay, and C of x, or the range set of C, should be a proper subset or the full set of x double star. Now, since C is linear, C preserves the structure, and if C is a map from x on to some RC, C is actually a bijective linear map, or a bijective map which preserves the structure, which means that C is actually an isomorphism from x onto some subspace of x double star. Okay, which means that the properties of x and RC are the range set of C, which is actually a subset of x double star RC, or in other words, there exists a subset of x double star which looks exactly like, or which has the same property of x. That's the meaning. That's why we use the embedding, the concept of embedding, which means that using this canonical transformation, we have actually found a space in x double star which is actually similar to, or has the similar property of x. So x is embedded onto a subspace of x double star. That's what this canonical embedding is actually means. So since C is a linear operator, if C is defined with respect as this is actually a bijective linear operator, which means that it is actually an isomorphism, which means that there exists a space which is a subset of x double star which is exactly same as capital X. So a copy of x is actually in x double star. That copy may not have the same elements as X, but it has the exact same property as X because there exists a mapping. That mapping is the canonical mapping which maps X onto some subspace RC, which is a subspace of X double star. So there is an exact copy of a vector space X in X double star, which is actually quite a revelation because X double star consists of set of all linear functionals defined on X double star. X is actually a vector space. So a copy of X is in X double star means every element is related to some linear functional. That's a quite a theorem in itself. So a copy of X is in X double star. That's why we use the concept embedding. It is embedded onto X double star. And that's why this map C is called canonical embedding. There are some cases in which R of C should be exactly is X double star. There are some cases, or the range set of the canonical map is X double star itself. In such cases, the vector space X is called algebraically reflexive. X is called algebraically reflexive, which means that X is exactly has the similar property as X double star. Okay, even though the elements are not same, there's a linear map which maps onto X double star because range set is X double star. So both the spaces are actually isomorphic, which means that exactly same. Though X double star is actually a copy of X star, which is defined differently but has exactly the same property. Now we are actually in the next section we are actually trying to observe some algebraically reflexive spaces, vector spaces, and the important result is that if X is finite dimensional, then X is algebraically reflexive. So every finite dimensional space is actually algebraically reflexive, which means that on every finite dimensional space is algebraically dual is completely characterized. Our objective was to understand something about algebraically second algebraic dual, and the second algebraic dual is completely characterized in the case of finite dimensional space. So the space is algebraically reflexive, which means that X is exactly same as X double star. So its second algebraic dual is actually same as the vector space. Okay, that's the important theorem which we are going to prove. So these are the some important definition which is essential for our study. So I hope you understood. Thank you.